When you picture Mars, you probably imagine a dead, dry, red desert. However, that is not what Perseverance found sitting at the bottom of Jezero Crater, a fossilized river delta identical to ones found on Earth. Today, the Martian surface is an extraordinarily hostile, frozen desert. The planet is wrapped in a thin, fragile atmosphere where liquid water cannot exist on the surface. With a mean surface pressure of just over 6 millibars, less than 1% of Earth's atmosphere, any exposed pool of water would instantly boil away or freeze solid. The global average temperature hovers around a bitter -63 degrees Celsius, and no liquid water has ever been observed flowing across this barren terrain. It is a world locked in a seemingly permanent icy frost, completely incompatible with the active, flowing water that once carved its vast dry valley networks billions of years ago. On August 6, 2012, NASA's Curiosity rover touched down inside Gale Crater, a massive 154-kilometer-wide impact basin. The mission was not designed to find active water, but to read the ancient geological record written in the stone. In early 2013, at a depression named Yellowknife Bay, Curiosity conducted its first drilling operations, targeting a fine-grained, light-toned rock formation known as the sheepbed mudstone. Engineers commanded the rover to drill into two specific targets, named John Klein and Cumberland. The pulverized rock retrieved from these shallow holes completely changed the understanding of Mars. Instead of volcanic ash or dry, wind-blown dust, mineralogical analysis by the onboard Che-Min X-ray diffractometer and the SAM instrument suite revealed a mineral mixture dominated by smectite clay minerals. These clays made up about 20% of the drilled powder. On Earth, such fine-grained phyllosilicates only form in calm, long-standing bodies of liquid water. The chemical analysis showed a neutral pH of approximately 7 and very low salinity. This was not an acidic, toxic environment, nor was it a temporary, highly evaporated salt flat. The evidence pointed to a stable, ancient, freshwater lake. For hundreds of years, this basin held water that would have been safe enough to support microbial life, directly challenging the assumption that Mars has always been a dry, barren world. The discovery proved that early Mars hosted quiet, habitable aquatic systems. The ancient lake at Yellowknife Bay was no isolated event. As Curiosity climbed the foothills of Mount Sharp, also known as Aeolis Mons, it encountered a vast, stacked archive of Martian history. The thick layers of sedimentary rock at the mountain's base rise hundreds of meters high, preserving a sequential record of lakes filling, drying, and returning over millions of years. This was not a temporary puddle, but an enduring, long-lived environmental basin. Inside these layers, Curiosity's chemistry and mineralogy instrument, Che-Min, detected high concentrations of clay minerals within the rock. Because these specific clays require sustained, long-term contact with liquid water to form, their presence throughout the deep, repeating stratigraphic layers of Aeolis Mons confirms that stable, wet conditions endured for vast geological epochs. Gale Crater represents an unbroken physical record of a world that once maintained a stable, active surface water cycle. On February 18, 2021, NASA's Perseverance rover arrived at Jezero Crater, a 45-kilometer-wide impact basin. Years before touchdown, planetary scientists analyzing high-resolution images from the Mars Reconnaissance Orbiter had flagged a prominent fan-shaped landform along the crater's western rim. From orbit, this feature closely resembled a terrestrial river delta, indicating that an ancient river once emptied into a body of water, dropping its cargo of sand and clay. However, Confirming this process required direct close-up observations of the stone itself. In 2022, Perseverance reached the steep stratified cliffs of the delta front, utilizing its advanced cameras to examine the exposed rock faces. The rover quickly confirmed what orbital data had suggested. Mastcam-Z captured distinct sedimentary layers stacked in thick horizontal sequences. Within these vertical rock faces, scientists identified cross-bedding, tilted sediment structures that form when strong water currents push sand grains forward along a riverbed. Beside these fine sand layers were coarse, rounded conglomerate rocks containing smooth, water-worn pebbles. On Earth, pebbles only lose their sharp edges after being tumbled and polished over long distances by the continuous flow of running water. Together, these features serve as clear signatures of flowing water depositing material into a standing lake. The scale of the delta allows researchers to estimate the physical dimensions of this extinct hydrologic system. During the Noachian epoch, roughly 3.5 to 3.8 billion years ago, Jezero Crater held a massive lake, measuring approximately 35 kilometers wide and up to 250 meters deep. A steady, powerful river breached the western crater wall, carrying sediment from the surrounding highlands and building the delta layer by layer over thousands of years. This fossilized environment stands as a preserved monument to an era when Mars was not only wet, but dynamic enough to maintain vast, deep lakes. In 2022, Perseverance's Sherlock and Pixel instruments identified organic molecules preserved within the ancient sedimentary rocks of the Jezero Delta. Scientists caution that these carbon-bearing compounds are not a definitive signature of past life, as abiotic chemical processes can also generate organic matter. Yet, their physical preservation inside the stone, when combined with the widespread clay minerals discovered by curiosity, reveals a far greater planetary story. This geological archive required the protection of stable, long-term liquid water to survive over billions of years. Together, these discoveries show that ancient Mars possessed an environment far removed from a frozen desert. The planet supported a fully functioning global water cycle. This active climate system included steady rainfall, continuous surface runoff, and standing lakes that persisted for thousands of years. While the evidence stops short of confirming Martian biology, it proves the ancient world possessed the sustained, hospitable conditions necessary to make life possible. Early Mars was more than simply wet. It had the potential to harbor life. Around 4.1 to 4.2 billion years ago, a silent catastrophe altered the fate of Mars. The planet's molten core cooled, shutting down its internal magnetic dynamo. Without this active dynamo, the global magnetic field collapsed, leaving Mars completely defenseless. The solar wind, a relentless stream of high-energy particles from the Sun, began directly striking the upper atmosphere, stripping away its gases and venting them into deep space. Since entering orbit in 2014, NASA's MAVEN spacecraft has measured this ongoing destruction. MAVEN's instruments reveal that solar radiation continues to erode the remaining atmosphere, a process that dramatically accelerates during intense solar storms. The physical evidence of this ancient stripping is preserved in the soil below. Inside Gale Crater, Curiosity's SAM instrument analyzed the remaining air, finding a clear enrichment of heavier isotopes like argon-40 relative to argon-36. Because solar winds strip lighter isotopes more easily, this distinct chemical signature serves as a clear fingerprint of billions of years of atmospheric loss, revealing how a once wet world slowly bled into space. Today, The Martian atmosphere exerts a mere 6 millibars of surface pressure. Billions of years ago, during the Noachian epoch, that pressure likely exceeded 1 bar, a density comparable to Earth's atmosphere today. While the air has vanished, the frozen geological proof of a warmer, wetter past remains locked in the dry riverbeds, lake basins, and deltas scoring the ground. The physical case for an ancient active water cycle is written directly into the planet's surface. Yet, answering the deepest questions about potential Martian biology requires a closer look. Future missions aim to bring cached rocks of the Jezero Delta back to Earth for direct laboratory analysis. Today, Mars stands as a silent warning. Its dry riverbeds prove that habitability is a fragile, fleeting phase in a planet's life. As we await the first returned samples, we may finally learn if life is a cosmic anomaly or a universal certainty. Subscribe for more cosmic history.